Hello and welcome to the AutoRob course. This is lecture 8 on axis angle rotation on Quaternions. This is for University of Michigan course EECS 367, Introduction to Autonomous Robotics, and Michigan Robotics 511, Robot Operating Systems for fall semester 2020. I am Professor Chad Jenkins. And I will be giving this lecture. We're going to talk a lot about how we can start to think about how we can include our motors, or just provide the right foundation for including our motors and their motion into our forward kinematics. The forward kinematics we discussed in last lecture. Before I do that, I just wanted to say that once we get FK working, then we're ready to start Stylin. And so I want to start. So I want to suggest that you start thinking about how you can get your FK to start doing some great stuff. And I just want to show one example as we're moving from assignment 3 to assignment 4 that I think would be really cool. This is from Yi Yang a few semesters ago, and so he did this dance routine, which I thought caught my attention. Um, the beat it, there no, not funky. Oh, that was awesome! And so I thought, so this is the URDF model, the URF description that we got off online for the Boston Dynamics Atlas robot. And so Yi Yang, he implemented the forward kinematics from assignment 3, then included quaternions in order to get the motor rotation working. And then the next lecture, for lecture 9, we created a finite state machine to get it to do a dance routine, which I thought was great. So just so you know, I believe assignment 4 is coming, and I think, as much as I love what Yi Yang did, I think you can do better. You can definitely do better than what I've been able to do. So let me just show you my dance routine. So for my dance routine, I had the fetch, and I did this. And so there's a reason I'm in computer science again. But once I had my robot there, I turned on my PD controller, and then and my dance routine is this. And so this is supposed to be Saturday Night Fever, at least a very basic version of it. So you can kind of get play, get the disco going on in your head, wow 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 wow. It's this is meant to be a bass line. It's not. This isn't pro dancing. So I think I've seen some amazing dances during my time teaching this class. So I look forward to seeing much better from you. So when we're thinking about how we can get our robot to do better, we can come back to our forward kinematics checklist. And so in lecture 7, we talked about how given a kinematic description of the robot, the geometry of the links, how we can represent transforms as homogeneous 4x4 matrices, and then traverse the recursive structure of the robot to generate transforms for the position the robot properly in a common workspace. We covered all that in lecture 7, but the thing we held on to and left for later was thinking about the current state of all joints, so that we can consider the rotations of the motors. And then there was one more thing that we didn't talk about either, which was thinking about how we can choreograph the movements of the robot so that we can do dancing motions such as Beat It or Saturday Night Fever. And so that will be the next lecture that I cover on decision making architectures. And so when we're thinking about these types of robots, we just as a recollection, what we have when we want to define the kinematics of a robot, we're given the URDF. Or some sort of kinematic description that's shown over here to the left, and this includes so it lays out the robot. It tells which links are on the robot and how those links are connected together by joints. And remember, joints connect two links. And inside of each of those joint descriptions, there's an axis field, and so the axis says what is the axis of motion, either the axis of rotation or axis of translation that the parent body, the parent link can use to move the child link in its relative motion. And so for our real robotic systems, we should note that each of those joints has that the motion that's produced as those joints is produced by some form of motor. And so in this case, we can consider an electromotor of this kind. Those electromotors can both be able to produce rotational motion, which is sort of like so is sort of animated over here to the left for a brushed DC motor, and we call those Revolute joints. But they can also be used to provide a screw such that it can perform a translation motion that produces linear actuation, and that moves that can move translationally along an axis. And so we consider these, and so this is just showing diagrammatically in the middle what this looks like for Revolute and Prismatic joints. We should note that, I'm no mechanical engineer, I'm a computer scientist, roboticist with computer science in computer science trading, if you want to think about that. So other people make motors and they magically work for me, which is great. But if you want to know what's going on inside of many different types of actuators, such as your electromotor, there's some sort of physical phenomena that is producing motion about this axis. So in this case, we have the magnets are essentially using the repulsion of magnets based off of their polarity in order to produce motion, and then they repel and then attract to each other, and we can send current through these magnets in order to produce this motion. I'm going to stop right there and keep going. And we should note that there are different types of electromotors. I just showed a brushed DC motor, but usually you have a brushless DC motor. And so there's a great video here that goes into some of those differences. But assuming that there is some actuator, whether it be electromotor, hydraulic, pneumatic, which is air-based, maybe you have a polymer actuator that uses chemical reactions to produce motion, you're using some other phenomena. Once you have something that can produce motion, how do we include it into the forward kinematics and represent that motion, assuming that we can sense it and that motion is produced? And so what does it look like to include this in our matrix stack and then rotate about an axis? And so let's go back to our matrix stack, our recursive matrix stack formulation that we talked about in the previous lecture, and just think about that one more time with now considering the motion of motors. And so in this case, we're going to try to revert. This is the kinematic tree that we get from our URDF example. And this is our matrix stack here, and then we have the workspace shown below. When we get to the world, we're going to go through the global coordinate frame. We're going to push onto our matrix stack a copy of the top of the matrix stack whenever we hit degrees of freedom. And then we're going to multiply through the transform of the base frame with respect to the world frame. Once we get to the actual, once we get to the actual base link, we can then use the transform at the top of the matrix stack to be able to multiply out and give us and multiply the vertices of the link geometry out and place it into the world. We can get to our first joint, and with that first joint, we can place the joint with respect to its position and orientation with respect to its parent, and so we can multiply that to the top of the matrix stack, and so that's the positioning of the joint with respect to the position of joint 1 with respect to link 1. That's great. But now let's assume that we have there a prismatic, we now have a prismatic joint, right? So now this is a translational joint. We want to include that into our matrix stack representation. So how do we account for the motion of joint 1, which is given to us by degree of freedom D1 right here? Well, it's actually pretty simple. We can just multiply the motion of the state of that some matrix that accounts for some transform that accounts for the movement of the motor degree of freedom using the state. And so if we have a translational motion, it's very easy to account for that motion. We're just going to take the axis that we have here for this joint, and we're going to pose it as a translation matrix. So now what we'll do is we'll take the top of the stack will represent all the matrices, all the transforms that got us up to that represent joint 1 with respect to the world. Then we're also going to have this this translational matrix that represents the state of the joint, and so how much the joint is inducing translation. We can take the top of that stack and just store it with the joint 1 transform, and that will give us this matrix right here. So it's just simply scaling the motor axis for this translational effect. Great. So we're moving on. We consider that this is our link 2 transform, just to show it out there what that looks like for the vertices again. We multiply the vertices of link 2 through. We get this common. We're essentially performing this entire multiplication here. So that's working. And so once we process link 2, we pop and go back to link 1, and then we're going to process the second joint. So when we get to the second joint, we push everything back up again. We're going to place the joint. That's going to be the third frame. We're going to place that third frame with respect to link 1 to link 1 frame, and then we get joint 2. But in this case now, when we have joint 2, it's going to be Revolute. So this is something that's going to be revolving around our motor axis, which could be any unit vector. And so how do we account for the motion of joint 2 if we just if we want to have some rotation that we right multiply onto our matrix stack? Well, if we have we can use some sort of rotational matrix that's going to represent the rotation of the angle about this axis. So we have an axis that is the axis of rotation. We're going to get some value that's going to be the angle that we want to rotate about. And so we could form that rotation matrix and put it on. And if we can do that, then we've accounted for the motion of the Revolute joint. However, this may be a bit more tricky than our translational case. And so how do we perform this rotation? The first thing we could try is, if we remember how we handled the roll pitch yaw of the joint, how we place it with respect to its parent. We used Euler angles to do that. Importantly, Euler angles have a number of problems that we should consider. First, let's consider an example where we have what we call ZYZ Euler angles. And so I just found this example online. I found it to be helpful. And so with the ZYZ angles, let's just take a look at this case right here. So let's start off and consider that our axes start off aligned with X, Y, and Z, right? And what we're going to do is perform consecutive rotations about Z, the Z axis, then the Y axis, and then the Z axis again. And maybe that'll be a way for us to express this rotation. And so just walking through the example, we'll overlay. I overlaid in red our initial X, Y, Z axes. And our first step is going to be to rotate about the Z-axis. So I've made the Z-axis dashed right here. And then if I rotate the other two axes clockwise by alpha, that will give me a new rotation. Now note, this is really important. This Y that was the original axis that I thought I was going to be rotating about, I'm not rotating about that axis anymore. I'm rotating about this new Y axis right here. That is now the result after performing this rotation. So even though I think I'm rotating about this Y that was the original one, I'm not rotating about it because I've moved that. This rotation induces a frame change. But once I've done that, so now if I want to rotate about my new Y, I can rotate about that in terms of beta. Get about the angle beta. And then I get a new frame, and then if I rotate about Z again, I'm going to get another new frame to get my final axes. But this frame change the change of frame that's induced by each of these rotations is actually really, really problematic, and it kind of prevents us from just doing the straight axis angle rotation in a straightforward manner. And so here's just an example. I took that off the web, but you should note, and just for some of so if you want to work through the math, but important, we get a new frame every time we rotate, and that can be tricky to deal with. And one reason why it's especially problematic is that we might end up with certain conditions that are not so good. So consider a gyroscope. A gyroscope can represent these Euler angles, and so every successive, as we get further inside of the rotation order is defined by the size of these of the rings, and so the outer ring influences all the rings inside of it, and so the gyroscope and so these rings actually represent a rotational axis, and so we can consider that the object that's inside is being this gyroscope essentially performs like a gyroscope of this form performs like doing an Euler angle. An Euler angle rotation. But I'm especially concerned about this case right here. And so because this case is concerning, because what it represents is something called gimbal lock. So gimbal lock occurs when two axes are aligned. So you can see that the gimbals that are associated with the blue and the green rings right here are now in alignment. And so what happens is this reduces our 3 degrees of freedom that we originally thought we had down to 2 degrees of freedom, based off of the axis order that we've chosen and the current angles that we're rotating. And so gimbal lock is more than just a problem than an inconvenience. It could be a major problem. And so what's one reason why gimbal lock might be a problem for rotation? I'm gonna let you think about that while I go get a drink. You just get it? All right. So actually what it turns out is that we could have, we may not have our full complement of linearly independent axes at that point. And so if we wanted to do something like compute an inverse of a transform matrix, that might be really problematic when we do this. Not to say that that's the only reason, but gimbal lock can be very problematic in this case. This is one of the extreme cases where we have where we can introduce real problems. And so just a few examples I just wanted to throw out there for you to consider on your own or with inside of your study pods. Consider a rotation with these axes. Assume that the second rotation, beta, is pi over 2. And so you can work through this, and then you can see that we can get that when you try to then multiply by a vector, it could be really problematic. There's one that you can just do with your body. Usually I do it in class, but because we're remote this semester, you'll have to just catch me at a time when we'll do it together. So one thing that I think could be more interesting is to rotate by an axis. And so one thing that you consider is that my kids are really good at doing this already because of their fidget spinner. So I have a fidget spinner right here. This is my NASA fidget spinner. I'm gonna just bring that close. I also have one that lights up too, so I can turn that on. So I got my light up fidget spinner. Did it not light up? It's a little old, so we'll see. And so what these really represent, you should think of this as really sort of your axis angle rotation. So if I took my fidget spinner and then just spun it, right? So now I'm considering motor rotation. Or not motor rotation, I'm considering just rotation that I produced about some arbitrary axis based off of where about the vector that's perpendicular to my fidget spinner. And so how do I represent that kind of motion? So Rodrigues gives us a very interesting approach to think about how we can do axis angle rotation. It's very clever. So what Rodrigues says is that given two vectors, A and B, and A has to be unit length, the same unit length that we're assuming that our axis vectors are going to be in our URDF file. And so if we have these two vectors, what we want to compute, what we want to infer is the angle B prime that results from rotating vector B around around A by angle theta. And so this is what we want to produce from this axis angle rotation. One of the key ideas of this is that we can take vector B and break it down into two subvectors, and so so we can break it into B parallel, which is going to be represent B onto the vector A. And then we're going to have B perpendicular, which is going to be orthogonal to, which instead of being parallel to A will be orthogonal to A. And we should note that if we take these two vectors, B parallel and B perpendicular, and we add them together, we should be able to reconstruct the vector B itself. So once we do that, we want to consider how we can compute these. So what's an operator that you can use to compute B parallel? Think about it, or pause the video. Remember linear algebra? All right. We could think of this as a vector projection. So we can represent that as the product of A times AB. And so this is going to give us B parallel. Can we figure out a way to express B perpendicular as through cross product operations? Think about it again. It's actually really interesting. It took me a while to come up with this myself, back when I was originally looking at this. All right. We can think of it as negative A cross the cross product of A and B. So you have to look at it a little bit, but if you think about it, we can get that cross product. So if you take A cross B, right, you'll get a vector that's perpendicular to that. And then if you take that vector perpendicular to A and A cross B, then you can get B perpendicular. Pretty smart. So we should note that if we're rotating B about A, right, that B parallel is not affected by that rotation at all. Only B perpendicular is. And so that gives us that means that we can rotate this, we can perform all these rotations that we want, and B parallel stays in place. And so if we can rotate B perpendicular around A, right, by our angle theta, then we can get if we can get this B perpendicular prime, that is this rotated version about our angle theta, and then come back and add our B parallel to it, then we've got our B prime, which is going to be our rotated axis, and that would be great if we can do that. What makes us think that we can do this rotation B perpendicular around A? Well, it just depends on how you look at it. So if we're looking down from A's perspective, down the positive axis of A, what we'll note is that we get this sort of viewpoint that we see here on the right. That we find that there's this plane that is orthogonal to A, that's defined by A cross that's defined by B perpendicular on one axis and A cross B on the vertical axis. And so if we consider those our elementary basis functions, then really what we need to do, then all we have to do is use a little bit of trigonometry to then rotate our vector, our x-axis by our angle, and that will give us our B perpendicular prime. And we should just note that we can get this directly if we just, and so we can get this directly from just looking at considering these are our basis our basis axes. That comes directly. They give us these our elementary axes, I should say. That gives us I'm gonna duck down for a little bit. And so that gives us our expression of what this vector is, what it is directly, which is great. So now if I take that expression that gives us B perpendicular prime, and then like we said before, if we add B parallel to it, then we get our rotated rotated b prime vector right here, which is fabulous. So once I have that, it would be great so that gives us our basic expression of the Rodrigues rotation formula. Now I'd like to be able to get rid of these B parallels and B perpendiculars and get something that's just expressed with respect to A and B, so I don't have to do weird computations and do these things. So what I can do is then try to substitute out B perpendicular. And so I can do that in my next step right here, and we see that. We'll then group terms by B parallel, and then substitute out B parallel, and that gives us our Rodrigues rotation formula that we have right here. And so we can use this to form a rotation matrix as well, I should say. And so just noting that we need some operators that we pull back from linear algebra. So if we want to compute this U bracket X, which is a skew symmetric matrix, that's in order to perform usually used to do a cross product. But that skew symmetric matrix is this operator right here, and I'm just a refresh right here of what a skew symmetric matrix does. And then this operator right here is an outer product, and so that's just taking our axis and then taking the outer product of that. And so I'm just this is just a refresh. This is just so you know. And then in the end we get a resulting rotation matrix that's of this form right here. This can get a little messy, so maybe there's a cleaner expression of axis angle rotation that we could use instead. And fortunately, there's some ideas that have come from mathematical literature, such as rotation by complex numbers. So when we're thinking about how to represent a rotation, so let's just think about in two dimensions right now. A complex number basically has a real and an imaginary component, where the imaginary axis can it multiplies that scalar b by the square root of -1 that puts into the imaginary space. We should note that in this combined real imaginary space, this 2D real imaginary space, the vector AB is a unit, can be expressed as a unit vector, and then you have a rotation angle theta that can be maintained. You can if you think about this angle representing a rotation, you can use Euler's formula to encode it, and then if you want to multiply two rotations together, you can use Euler's formula to combine those and compose rotation. And so this is one quick way of thinking about how we can think of 2D rotation in the complex number space. We can generalize that thought into 3 dimensions by thinking about a quaternion. And so it performs axis angle rotation. It provides a clean mathematical expression. And we should think of this, instead of having just a circle in 2D, now for 3 dimensions we're gonna consider the unit sphere in 4 dimensions. And so all of our rotations are gonna sit on this this unit sphere and represent a particular rotation. Every point's gonna represent a particular rotation. Quaternions were the inspiration, the flash of genius of Hamilton, and so Hamilton just got the idea and carved it into a tree. There's a great story there. I'm gonna let you read up about that. But just so we note, so quaternions in 3D. So now we have to have we're going to use 3 imaginary numbers that provides a basis. And so you'll have this 4-dimensional space is going to have 1 real dimension. It's going to have 3 imaginary dimensions. We should note that these imaginary numbers, they're not not standard imaginary numbers, right? They don't sit on the real number space. But what you should note though is that if we take the square of any of these numbers, that they should equal -1, and they have to be they're not I, J, and K, which are going to be these numbers for the basis, these imaginary numbers. They're not the same number. So sometimes people make that mistake. But if we multiply, if we took the square of them, they will equal -1. Additionally, if we take I times j, we will get k. If we take j times k, we get I. If we reverse and k times I, we get j. If we reverse their order, we get the negative of those. And so this is a 3D. This performs a real 3D basis, or this forms a 3D basis. And given that, now our complex number as a quaternion is defined as with 4 terms, right? So we have a real component, an I component, a J component, and a K component. And those last 3 are and so we can take each of those terms and put a scalar on them, and then we can and this will break down into a real and imaginary vector. So if we think of A being our real component and B being scalars on our imaginary component, we get a real and a imaginary vector that produces. And so just note, in this case, we're using Q to represent quaternion, even though typically Q is going to be a configuration for us. One thing that makes, so we should note that if we have a vector space, that means that we have to have certain operations that will produce certain operations that our space will be closed to with respect to. So we should note that quaternions has 3 operations: addition and scalar multiplication. If we perform that addition or scalar multiplication, we will get another member of the quaternion set, which makes us a nice vector space, which is great. And additionally, we can do quaternion multiplication, which looks like this up here. We should note that the quaternion multiplication does not commute, and so we should remember if these represent rotations, that means that whenever we apply rotation, we're changing the axes of our frame, and so we can't commute those. There's certain properties that we should remember of a quaternion. So there's a quaternion norm, which is going to be the sum of the squares of the individual scalars. There's a conjugate quaternion, which is going to be the negative of the imaginary vector. The inverse quaternion takes our conjugate quaternion and divides by the squared norm. And then our unit quaternion is going to have a norm of 1, and then the inverse of the unit quaternion is just going to be our conjugate quaternion. When we want to perform a rotation by a quaternion, we should note that quaternions are that again is a point on the 4D unit sphere, and so when we want to encode a rotation as a quaternion, what we'll do is we'll take our unit vector, our rotational axis, which is going to be u, and we're going to break it into its components ux, uy, and uz. Then we can take that rotational component and then put it into the vector that's up there, where we use the half of the angle that we want to rotate by. So the first element of this vector is going to be cosine of this half angle. The second element is going to be the x component of our rotation axis, ux, times the sine of the half angle. Our next component is going to be uy times the sine of the half angle, and then uz is going to be times sine the half angle. We're not going to explore this in this class. We're not going to implement this class too much, but we can rotate any point by the unit quaternion by performing a process that's called conjugation. And so what we can do is construct any point as a vector that has a 0 for its real part, and then uses the point itself as the imaginary vector. And then we can if we execute this expression that you have here, you can then generate a rotated. You'll get a rotation of that point by the quaternion that results from the conjugation process. And so this is something that's helpful, and especially when you start to compose rotations together. This is just an example I made in MATLAB several years ago. You can feel free to look at it. I have to resurrect that code at some point. So checkpoint. What is the unit quaternion when there is no rotation at all? Well, it should be an identity quaternion. So we have no rotation. So cosine of the half angle should lead to a non-zero value, and the sine of the half angle will be 0. If this quaternion is now unit length, we'll get 1 0 0 0. 1 in the real, and then zeros for the imaginary vector. What about if our rotation is 180 degrees about the z-axis? Well, there's only going to be rotation about the z, and so we'll get an expression that looks like this. What about rotation 90 degrees about the y-axis? Well, then we have to consider that there's only going to be rotation about the y-axis, but we also have to consider that the cosine, that if we evaluated cosine of the half angle, we'll get some non-zero value. The same thing for the y component, and so we'll get something that looks like this. And this will also apply when we consider negative 90 degrees about the x-axis as well. So restating quaternions, just so you note that that a quaternion and its negative give the same rotation. We can compose quaternions together using the multiplication. And just remember again, 3D rotations do not commute. 2D rotations do commute, but 3D does not. There's an equivalency between Rodrigues axis angle and quaternions. I'm just flashing this up for you to see it and have it. The slides are online. And so we can, whenever we have a quaternion, we can convert that to a rotation matrix. And that's what we're going to do in this case. It's probably a little it's probably inelegant, but it's this quickest thing we can do for this class. And so so imagine that you have a quaternion with 4 elements that we have here, and then we can take each of those elements and put them into one of these two forms to get a rotation matrix. And so this is going to be a 3x3 non-homogeneous rotation matrix that we need to then put into a homogeneous transform. We should also note that there are you can also convert a rotation matrix to a quaternion. So if we're coming back to where we left off with forward kinematics, what we should note is that when we want to then consider the rotation of a motor about an axis, what we're going to do is form a unit quaternion based off of the axis of the joint and the motor and the current motor angle. And we can form that into a quaternion, and then we can take that quaternion and then plug it into one of these forms to just do a conversion. And then when we take those, we can then use that to form our rotation matrix here that we multiply onto our stack. And so that should allow us to perform this arbitrary rotation about an arbitrary axis, which then can be used to put link 3 on. Once we have link 3 on, we can then do the same thing for joint 3, which might be a rotation axis itself, and then put joint 4 on, and that gives us our URDF example, and so we then pop off of that. So now we should be able to, inside of our forward kinematics, consider the state of all joints, and then be able to render that out. So now what you're seeing is the same URDF example that we just went through. This is just the version of it live in Knievel, and so when we're looking at this, we can rotate any of the joints, and so this is joint 1. We can rotate this, and so note that we're rotating about the axis that's over here. Similarly, we can move over and rotate this joint right here, and so this is just a rotation of this joint, and we can move that to anywhere that we'd like, and so that moves all the child joints, and so then we can go up and rotate this joint as well, and so now we've been able to have this work for any of for this URDF example. I'm going to go over and try our MR2 robot, and so I should be able to rotate these joints as well, be able to move them wherever I would like. I'm going to move it this way. And so now we can pose the robot in whatever pose that we would like. My fetch robot's still doing Saturday Night Fever. I'm going to stop it from doing that. and just move it back to our default pose right here. And so you should note that this has a prismatic joint on it as well, so we can move it up and down. But then I can also rotate the arm a bit and pose it any way that I would like as well. I'm going to move it that way. And then we'll come back down and let's see if we can move the head. So now and we can move the head as well. I can move that back and forth. Let's make it look up at so it's going to look at its hand. And so now we can pose these robots. We have the ability to express motor rotation inside of our robot, which is great. So with that, we can consider the current state of all of our joints. We can now include that into our forward kinematics repertoire. We've got our checklist mostly down, and then we'll go to reactive control. So we can start from these poses, we can then start to choreograph. We can start to lay out larger choreographed motions or routines. They could be dancing, or it could be some more purposeful task. But we'll cover that in the next lecture. And so a few considerations that we should keep in mind. One is, can a joint move infinitely far? The answer is, in some cases that's true, but for our fetch robot, definitely not. And so we have to respect joint limits as well. And so when we're considering our joint limits in the URDF, you'll find that. So you'll see a limit field. So usually this is the limits can provide limits on the amount of force that can be produced by the motor, velocity, upper bounds on the velocity that can be produced, as well as the upper and lower, which is the bounds on the state that the joint can take. So for instance, a prismatic joint, it can lower to I think 0 meters and move up to 0.4 meters. A Revolute joint, which such as the sort of shoulder that's there, this shoulder pan joint, it can only move between negative pi/2 and pi/2, right? So we need to make sure that we respect those joint limits. Some other important notes that you want to consider for the code stencil, rotation order, XYZ. Please remember that. You have to also implement vector cross, which we use for this, which will be used across multiple different aspects of the code, but is also used sort of behind the scenes to make a number of things work, such as the joint cylinder rendering. You have to implement base control so we can move your robot around properly. The origin field, so we use that to store things about the origin, but it's mostly used for debugging and providing important information about the joints with respect to each link. And we just assume for this case that a joint and its child link will share the same coordinate frame. And so just wanted to just say those. The vector cross, so if you don't implement vector cross, you get joint cylinders when they're rendered. It goes that way. With joint cylinders when they're rendered that are not aligned with the joint axis. And so if you implement vector cross properly, we will do the code stencil will do the alignment of the joint cylinders for you. When you move in the robot around in the base, we use WASD controls, and so we should be able to move the robot around the base. So let me just give you a quick example of that. And so, oops. And so for our MR2 robot, I should be able to press W and have the robot move forward, have the robot turn in place, and then also move side to side, and just be able to move anywhere that we'd like to go inside of this. So WASD controls. I should be able to move the robot in any direction, forward, backward, left, right, and turn in place, or some combination of all of those. And so those base controls should work. in order for your base controls to work properly, you have to make sure that you provide robot heading and lateral for us. And so that robot heading and lateral is computed by taking the point in the base frame of the robot. So if you consider what the unit point that's in front of the robot in terms of its heading direction along the x-axis, right? Or z-axis, depending on which coordinate system you're using. If we transform that into the world frame, the code stencil will do the right things to make sure that you can move the robot forward and backwards. Same thing for the lateral. So if you use a unit point that's on the side of the robot and the robot's base frame and transform that into world coordinates, we will do this. So the code stencil will do everything it needs to make the lateral motion of the robot work as well. And so before we stop and finish off with forward kinematics, I just wanted to go back and talk about some other ways that we could use to define the kinematics of the robot. Just revisit this really quickly. And so one of those, so there are a number of alternatives for forward kinematics that we could think about. One of those is Denavit-Hartenberg convention, and another of those is to consider screw vectors. And so if you want to take the traditional approach to representing forward kinematics, that is the DH convention that we have right here. Denavit-Hartenberg essentially represents our each local transform as a collection of four transforms, 2 rotations and 2 translations. We can parameterize these as thinking about a rotation, about a joint angle rotation, a link offset, a translation about a link length, and then also a link twist. We should note that for any type of motion, only one of these parameters will be variable, and the rest will be constant. So if we perform a rotation, the joint angle will be variable, but all the others will be constant. And if we think about if we're trying to do a translation, only the link offset will be variable, and the link and everything else will be constant. And so we can multiply all of these together and get one homogeneous transformation. So if we use DH notation, then what we get, the way we describe our robot is through what's called a DH table, which then will give, so if we fill out the DH table for all the parameters of a robot, link length, link offset, joint angles, link twist, then we can, then essentially we've described the kinematics of the robot. I would say that creating these tables is not necessarily the easiest thing to do. DH takes a long time to get your head around, but once you have it, it just feels natural. And so this is just one example for a 3 degree of freedom robot arm. DH has certain properties that are really that make it very useful. So if we consider our child frame here, frame 1, with respect to our parent frame here, link 0, there's 2 properties that DH maintains. It says that the x-axis of frame 1 will always intersect the z-axis of the parent frame, and also that not only do they intersect, but they will be perpendicular. And so so these 2 properties essentially allow us to make this for that hold in order for DH to work. And so if you just work through if you work through each of these each step, going from the frame 1 into frame 0, you can just manually go through each of these and see how they hold. So I find that this picture from the Spong book was really helpful for me to understand Denavit-Hartenberg. We should note that if we use Denavit-Hartenberg notation, so we have to know there's a frame assignment process that also has to happen. So we know where the z-axis is always going to be aligned with the joint axis. So now it's not going to be a separate z-axis for the joint that's different from our axis of movement. Those are going to be aligned. And so now we know what these z-axes are, and so we have to attach frames to each of these z-axes for every joint that frame, we have to do a frame assignment process. But once we do that, then DH will work nicely. And we should note that through DH, it's not always going to be the case that the origin of these frames are going to sit inside of the joint itself. Sometimes it could be translated off of these frames. And so there's certain benefits to DH. There's only 4 parameters to consider, whereas if you look at our matrix stack representation, there's 10 parameters that we have to consider. You compose 4 matrices together, but they're pretty easy matrices to compute as opposed to 3 for the matrix stack, because we still have got to think about the quaternion, a number of other things there. But probably the biggest thing that's at issue is that with DH you get uniformity in the frame selection. There is no sort of ambiguity, free parameters around it. It imposes a certain structure that can be reliable, as opposed to the matrix stack where we have much more flexibility, less discipline, but more choice. And so with DH, the link frames are necessary for the computations. And our approach, for matrix stack, you can give or take it, but it means that we have to do more bookkeeping for this flexibility, for maybe a greater sense of intuition, whereas DH imposes a structure, but can take some time for people to get their head around. But in both of these cases, we still have this awkwardness of how we deal with both translation and rotation in sort of a nice, easy to understand sort of way. The matrix stack in particular, DH is more sort of an intuition issue, which is why there's been more interest in being able to think about more elegant approaches to represent both the translation and rotation of a local transform. And so there's been dual quaternions has been a more recent way of how robotics has been thinking about these types of transforms. The essence of it is that the same way that we expressed rotation in a complex space, we're going to do that. There's a dual complex space that can represent both rotation and translation. So we have to bring in the concept of a dual number, which means that you have some number that has a plus epsilon b, where if we take epsilon squared, we get 0. I will just say that it takes some time to think about what that could be. If you take the square of a number of something and get 0, what does that mean? If you have that, you can express a dual quaternion as a regular quaternion q plus epsilon times a quaternion prime, q prime. And so we have a real quaternion and a dual quaternion in this case. We should note that similar to our basic quaternion, we have operations for this vector space that for addition, scalar multiplication, and multiplication of 2 dual quaternions. But if we can do this, there's a great paper by Kostas Danilidis that says that that I go to as sort of my reference, but every rigid motion can then be expressed as an angle about an axis with direction and then a subsequent translation. And so our dual quaternion that we have over here can represent both that translation and rotation as a rigid motion. And then we can do that transformation about do these rigid transformations using a conjugation process right here. If you want to know more, I would suggest reading Professor Danilidis' paper. There's also a great paper by Wainwright. It's just sort of more a tutorial style. This is how you use dual quaternions. And so I think this is really, really interesting. So with that, our next lecture is going to talk about finite state machines and how we can start to get our robot to dance now that we have FK working. There's a great video of an HRP2 robot doing dancing. I'm wondering, so I would like to be able, so I'd love to get a definition of this robot up and running and having it do interesting dances, and we'll talk more about some of those interesting dances next time. Thank you very much for listening.